Welcome to UVU CS3060 Lecture 3.1, where we talk a little bit about process scheduling and how process scheduling is managed within an operating system. So as I stated in the previous lecture, we need to maximize CPU use. We need to quickly move from one process to another in order to make the operating system, or make the system in general, look efficient. We will use, or an operating system uses a process scheduler to decide between different processes and to make that particular context switch. Now, the process scheduler maintains different queues. We've talked a little bit about these queues. We have the job queue, which is all the processes within the system. This includes running processes, ready processes, waiting processes, everything. We have a queue for ready processes. These are the processes waiting to be executed. We have different device queues. Each device queue represents a set of processes waiting for I/O on a particular device. And device queues can include other waiting queues, such as concurrent access queues, waiting queues, as well as manually started sleep queues. Processes will migrate between the various queues, and this will be done by the process scheduler, as well as other activities. So, for example, the process scheduler moves a process from ready to run. The system call moves a process from running to wait. The exit system call will move a process from running to terminate, etc. And hardware interrupts can move processes from a wait state to a ready state. Here's a graphical example of some queues where we have a ready queue that has process 7 and process 2 waiting, keeps track of where the start and end is. You should know how to work with linked lists. This is a fairly important data structure within operating systems and within computer science in general. Here's a queue that doesn't have any processes. The magnetic tape, both magnetic tape units don't have any processes waiting. But here we have a disk unit that has 3 processes waiting. And then a terminal device that has 1 process waiting in it. So when it comes to queuing up, you can see here kind of a modified state diagram. We have a ready queue that has jobs coming into it, could be from a new state or from a CPU state. Maybe the CPU state will loop back to the ready queue. But in general, the CPU will move a process from its running state into one of several different states, such as time slice expired. Let's say a timer interrupted the CPU and said that process is done. The process will run through time slice expired and end up in the ready queue again. A process can also execute an I/O request where the I/O is executed and it returns back to the ready queue. CPU can also perform a fork operation where it actually creates a new process. In this particular case, not only does the parent process run through this child execute and return to the ready queue, but this child executes will create a new process. And that process will also be added to the ready queue. You will actually be exercising this fork API in assignment 2. There are different types of schedulers to be aware of. There is the CPU scheduler, which is used to choose which process should be used on the CPU. This is the scheduler we've been talking about so far. It goes to the ready queue, decides which process needs to be switched in, and then performs the context switch for that process. Sometimes it's the only scheduler on a system. We usually have scheduler operations very frequently within the millisecond range. And so our short-term scheduler must be very fast. There's also a concept of a long-term scheduler. In the case of long-term schedulers, this is actually deciding how processes should be managed within the various queues. Usually a long-term scheduler is more of a high-level administrative process, very infrequently executed, sometimes within the minute range, in fact, and is allowed to be slow. It can go ahead and take its time figuring out what it's going to do. But very often, the long-term scheduler is what manages things such as the degree of multiprogramming. Multiprogramming, if you remember, means having multiple programs in memory, which means the long-term scheduler decides which program can be loaded and which program should be unloaded for the time being. If a process needs a program to be in memory, the long-term scheduler will make sure that that program is in memory so the process has access to its data. Now, when it comes to scheduling, it's very important to consider the type of process we're dealing with. There are processes that generally do a lot of I/O. For example, when you have a shell program that is waiting for user input, that shell program is waiting for keyboard I/O. Now, in terms of what a CPU sees, a CPU runs very, very quickly compared to us slow, dumb humans who work at a glacial pace compared to the CPU. In the case of console programs, those are I/O-bound processes and usually only come in very quick CPU bursts. When you press a key, it needs to quickly do something with that key and then wait again. CPU-bound processes, on the other hand, usually stay on a CPU for long periods of time. Often these are very complex computations, long loops, programs that run for a long time without user interaction or without I/O. CPU-bound processes need to be managed differently than I/O-bound processes. In some cases, in a CPU-bound process, you want to give it as much CPU as possible, but you don't want to deny the I/O-bound processes, which need maybe not a lot of CPU time, but need very responsive CPU access. Maybe an I/O-bound process, because it's an interactive process, needs to be quick. There's nothing worse for a user to have to press a key and wait for that key to respond. What does your grandma do whenever something happens whenever they click on a button and it doesn't react quick enough? They continue clicking on it again and again and again. That's not a very responsive interactive system. And grandma is considered an I/O-bound system. So those processes, or the operating system, should be very responsive to those processes. The long-term scheduler is trying to give a good process mix. So there's also the concept of a medium-term scheduler, which can be used if you need to swap processes in quickly. The long-term scheduler can move a process out more or less permanently, but a medium-term scheduler will take a process out of memory stored on disk and bring it back from the disk quickly. This is called swapping. And so what we have here is we have processes that are running on a CPU that get swapped out and stored on secondary storage, such as a disk. those processes, which are not completed, they haven't finished their job, those processes, when it's time for them to be scheduled again, can be swapped in and put back on the ready queue, at which point that process will eventually run on the CPU. Frequently, processes that are in I/O waiting queues will be swapped out as well, because if a process is waiting for I/O, that process is not going to execute and can on the CPU and can be stored onto secondary storage. Now, we've been discussing this scheduler concept from the perspective of a desktop or a laptop system or a server system. This is very different from how mobile systems do things. Mobile systems usually only allow one, well, the early versions of iOS would only allow one process to run and nothing was allowed to be in the background. Everything was suspended. This has changed recently in iOS and is not the case for Android, in which case in those particular, in the latest iOS and Android platforms are allowed to run processes in the background. In most cases, a foreground process is the one that is controlled by the user interface at that time. And every other process is considered a background process, which may be in memory, but it will not be given all the resources that a foreground process, and will usually be severely limited in terms of CPU time, etc. Now, okay, I'm going to cut that section. So again, those limits include receiving notification of events, long-running audio playback. Sometimes those background processes use a service to perform a task, and services can keep running even if the background process is suspended. A service on a mobile device has no user interface and usually has very small memory footprint. So we talked again about context switch. A context switch is where we must save the state of the old process and load the state of a new process. Is represented by the process control block. But this is the important point here. Context switch time is overhead. The system does no useful work while switching. Context switches are necessary, but they are not good use of CPU time. Usually the more complex the operating system and the process control block, the longer the context switch. And a lot of times the context switch is time dependent on hardware support. A lot of hardware actually provides multiple sets of registers per CPU, so that you can have multiple contexts loaded and switch between those contexts very rapidly. This is not the case for the Intel platform. This ends lecture 3.1, where we discuss the process scheduler.